All right, guys, I have 2:30, so we'll go ahead and get started. So welcome to week 5. So we're cruising right along, almost through the class because it's only 7 weeks. So outside of the classroom, I have posted a couple announcements there. Well, really just stuff for you. This is a book about Kevin Mitnick, and regardless of how you may feel about Kevin, I would say there's a bit of a debate there, but a lot of people view him as like the father of like pen testing almost. And so the Ghost on the Wires is kind of his story. Super interesting. I highly recommend that you listen to it. It's just an engaging story. I thought at least. Um, kind of professional development in this space. So that's posted there. It's in 2 parts because the file was so big. But it's all there. So let's take a look at week 5, introduction to networking models and protocols. Here are your outcomes. We have a little bit of reading in the book. So chapter 6, section 6.1. And if you have a physical book, the page numbers are there. But you can see, in the O'Reilly version, there's not page numbers. And so you'll have to follow section 6.1 until it basically says, hey, we're out of section 6.1. And then lecture. And then there is reference to OSI model in here. And I think week 4 also had some OSI model stuff, but we're going to get more into it here. So if it didn't make sense last week, and I probably said that in the lecture, was like, hey, go out, take a look at the OSI model. We're going to talk more about it next week. But the explanation will come in this lecture. So let's take a look at the quiz results for last week. Overall, class average was 92.17, which is phenomenal. That's way above average. Love to see it. And there's not even a single question on here that I'm necessarily concerned about for the class. Normally, my threshold is like below 70. And the closest one that we have to that's like almost 72%. So really, it's not bad, especially for a class of, I think you guys are like 136 or something. But I'll pause here. I'll open the floor. Did anybody have any comments, questions, or concerns on the quiz from last week? I know I received some email inquiries, but I did respond to those. Okay. I'll take
Professor,
it
can
as
you
there.
hold it?
Yeah. What's up,
Was
Shannon?
it hard? Hey, what's going on, Professor? Hey, was it hard? It's just you had to read the question. There was probably one or two that was let me think this through and best guess type. That was only
Okay. I
that's
hear
the
it.
only way I look
Yeah.
at it.
Yeah. For this class, especially if you have any prior experience, you can what if the questions so hard. And you really have to transcend that, right? Because this is a very entry level class. Like people with zero IT or even computer knowledge take this class. And so you got to almost think of it through those lens, right? And while you could what if a lot of the scenarios to death, um, you can't do that here, right? Like we're trying to teach like wave top concepts. And if you what if it, you're probably going to overthink the question. Does that make sense? Hopefully it does.
It does. It does.
Okay. All right, cool deal. Well, let me start showing you some of the extra material for this week. So again, we're focusing on networking, and there's this tool, sectools.org, and this website is specifically kind of focused in on networking tools. And some of these tools you're gonna dive in deep in this program, right? So for instance, Wireshark, the number one listed tool up here, we have an entire class, a 15-week class dedicated to teaching you how to use Wireshark and why it's important. And that's CYBV 326. That'll probably be yeah, I see Mike's in 326 now. But it will be in your course or your program plan. There's also at least one other course where you're going to touch Metasploit, and that's going to be CYBV 480. That's cyber warfare. And that's usually a student favorite because you get to do some pen testing on a company in the VLE. Nessus, if you end up taking 385, which it has some similarities to this class. You're at least if you take it with me, you're going to do a Nessus lab. If you take it with someone else, you're probably going to do a PGP email lab. But ultimately, what I'm saying is like a decent amount of these tools you're going to get your experience on here in the program. But one of the best things that you can do right now, if you're not already working in industry, is to go out, build a lab at your house, right? And it doesn't have to be like literal, servers and network racks of switches and routers and stuff, right? Like you can do this all virtually and have, a virtual environment that you build out, right? And you can start that with virtual machines, right? Play with different operating systems, but go play with some tools. That way you can put it on your resume and say, hey, I have familiarity with Metasploit, right? I want to be a pen tester. I understand Metasploit. Here's some things I've done with that, right? You need to be able to talk to it. And so this is just another way where you can go take a look at, industry recognized tools. The next one, specific to networking, is Cisco Packet Tracer. This is an amazing tool, really. And the learning is free. And so if you make an account here, it'll teach you how to go and download Cisco Packet Tracer. It'll teach you everything you need to know to get started on Cisco Packet Tracer. And the cool thing that about Packet Tracer is that it is so in depth that you like when you click on a device, it's like you're physically there. You have to turn the switch on by pressing the button, right? You have to connect cables to the switch in the router. And the free classes go over all that, but if you're looking at a networking career, this is one of the best tools that you can get your hands on because it has everything that you need. I mean, you can build out entire network architectures and communicate via it, right? Because you have on the switches and routers, you have access to the command lines. And it has really Cisco's entire suite of routers and switches and firewalls and all these other things. And so you can even log into like virtual computers so that you can ping across the network or do whatever you're trying to do, tunnel. So almost full functionality. Really awesome and powerful tool here. Let me drop this in the chat. Okay. So then the last thing I wanted to show you is this is straight from Cisco, and this is security features on switches. Okay. Now, routers and switches will both have security features that you can enable, right? But if we're, switches are really kind of the backbone of a network. Whether you're implementing virtual local area networks, VLANs, or you're buying physical switches to segment out your network, they're really like the workhorse, right? You might have what's given a smaller network or organization might have one router, but they could have 5, 6, 7 switches to be able to connect the different users in that local area network. And so it's very important to make sure that you have your switches configured appropriately. And so if this kind of work interests you, it would probably be very prudent of you to go take a look at, hey, what are some of the security features that we can implement on switches? I did drop that in the chat. And then the last thing, this is just kind of a cool thing, storage attached network or network attached storage. So SAN versus NAS, there's two different ways to look at adding storage to a network. And I'm not talking about just in your computer, like this is attached to the network. And so this article really kind of puts it out there in layman terms on the differences here. And the cool thing is that you can do this at your home network for relatively cheap. Okay. All it takes is, again, it'll walk you through everything you need to know. And there's plenty of YouTube videos. But again, this would be another thing that you could go and take a look at and say, hey, for part of my lab environment, I'm going to build out a small SAN or NAS, right? So that I can have some extra storage for everyone in the house. And it's going to be a learning experience for me to configure this. And you can, again, hard drives are ultra cheap nowadays. And, really not a big lift to go and implement this. So let me drop this in the chat too. And I'll pause here. Any questions, comments, or concerns? over anything that I showed.
Professor,
Yeah, what's up?
question. Um,
What you got?
I'm I am going like this is like the first step of my journey. The
Okay.
question is, does this apply towards the cloud computing portion?
Does this apply to what?
To the cloud computing?
Um, so building out a SAN or a NOS.
Yeah, or all of it, all the tools that you just sent, that you
Um,
showed us.
Nothing is cloud specific, but I would say that, cloud to me is more of like a kind of a buzzword, right? Because cloud is nothing more than just someone else's computers and storage. And so, can you use, let's say, Metasploit to go and do some pen testing on a cloud service provider? Yes. Now there's caveats to that, right? Like Amazon specifically has rules for how you can do pen testing in their cloud stacks. But like these tools are kind of ubiquitous. Could you set up a SAN or a NOS and then connect it, your friend to it from a different network? Yeah, you could implement something like that where they connect in, and technically that would be like definition of a cloud storage in that situation, which you're hosting instead of like Amazon. But if you're looking for to get specific into the cloud space. Some things I would absolutely take a look at are like almost all of the cloud providers have certifications on their stuff. AWS is going to be the most popular and probably best bang for your buck just because of how ubiquitous it is. But Microsoft has Azure, and GCP or Google has their own like cloud stuff. Alibaba has their own stuff. IBM has their own stuff, and all are going to have certifications for their stuff. But if you're looking for most bang for your buck, I would start with AWS. Does that help slash answer your question, Shannon?
Yes.
Okay, cool. And for you, if I remember right, Shannon, you're a Marine, and really for anybody out there that's a veteran or on active duty, if you look at Onward to Opportunity, that is a program ran from the University of Syracuse where they pay for you to go get a certification of your choice. And I want to say the last time I looked, they had a couple different cloud certifications there. They send you through the training, they pay for your certification attempt and everything. And then something to look out for the VA. The VA runs a program too. Gosh, what's the name of it? They've temporarily just discontinued the program. Oh man, I cannot remember the name of this. Hold on.
No, I just pulled it up. It says it's through, yeah, Onward to Opportunity to Syracuse, and it's
Yeah.
through the DNLO's Italian name, DNLO Institute for Veterans and Military. Yeah, that's it.
Okay. Yeah, O2O is a really good opportunity.
Yep, I see it. Okay.
Vet Tech is the other one by the VA, but like I said, they just ended this. Um, but something to kind of look out for just in case they re-enable the program because that was really good because not only did you get to go through training, get your certifications, but they also guaranteed job placement. But there honestly in cybersecurity, there's so many different learning platforms. There's so many different opportunities out there like it's kind of crazy, especially for veterans. And it's for educational opportunities. There's so many free platforms, right? I think I showed you guys in like week one, just a couple of them, like Cybrary and Pluralsight and stuff like that. Like Pluralsight's paid, but a lot of the other stuff is free. And you guys have access to O'Reilly, which is honestly one of the best online learning platforms that I've ever seen in my career. All right. Any other questions, comments, concerns before we get started on the material for this week? Okay, so let's get started. Welcome to week 5, Introduction to Networking Models and Protocols. Please take a second and look at what we'll be talking about this week, and then we'll go ahead and move on. All right, so let's start off with the OSI model, the Open Systems Interconnection model, right? This is a theoretical understanding of how information moves across a network ultimately, okay? And the OSI model is in 7 layers, okay? We have two distinct layers to the 7 layers. So it's broken out into lower layers and higher layers, okay, or higher levels. So the lower layers are going to deal with specifically like whether you're using Wi-Fi, right? That's RF radiation. If you're using electrical signals via like Cat5 cable or fiber optic cable, which would be like light actually. And then the chunks of binary data, the ones and zeros that are going across, right? The higher levels are going to deal with like, hey, let's make sure that we're managing the connections that we have. Let's provide encryption. Let's be able to put the data in front of the end user in a way that's legible, right? So that's like kind of how we're going to think about the OSI model. This is what the OSI model looks like. Okay. So at the top, we have application, right? And that's when the end user is able to interface with literally whatever, like your web browser, HTTP, right? Is what we're looking at there. And this stuff has to work sequentially as well. So as we go down this stack, the application layer is going to hand information off to presentation, then session, then transport, and you can't skip any of this stuff, right? Whether you're going down the stack or up the stack. Now, there's two different ways to memorize this, and I would highly recommend being able to recall this at any given time, right? But the first one, then I think it's pronounced mnemoniker, right? Um, all people seem to need data processing, right? That's one way to remember this. And that's taking the first letter of each one of the layers and putting it into something you can remember. Now, that's going top to bottom. Now, bottom to top would be please do not throw sausage pizza away. Okay. And that's two different ways to kind of remember the OSI model. So, some other things to kind of break out here. All on the right, we have the TCP/IP model, right? So, TCP/IP and OSI model are related, but they're different. Okay. They're trying to convey very similar information, but TCP/IP is how the actual implementation is. You can think of OSI as just theoretical. Okay. Uh, OSI is also kind of rigid, where TCP/IP can get kind of gray and squishy in some areas. Also, so to note here between the two different models that we have, network access is going to take up the first 2 levels of the OSI model. Whereas we have networking or internetworking for layer 2 of the TCP/IP model is going to correspond one-to-one with network in the OSI model. Host to host is going to be a one-to-one for transport. And then layers 5 through 7 of the OSI model are going to correspond to application in the TCP/IP model. Some other things to take note here. We have encapsulation, or PDUs is what we would call them, protocol data units. And so at the lowest level, physical, right, we have bits or data stream. At the physical layer, this is where you're like literally plugging in the cable to the router to the computer, and you're getting like electrical pulses on the Cat5 cable, light pulses on the fiber optic, right? Like it is nothing but ones and zeros, ons and offs. The data link layer, we have frames, layer 2. At layer 3, we have packets or datagrams. You'll likely see this mostly referred to as a packet. Layer 4, we have segments, and then 5 and above is just data. Okay, those are referred to as PDUs, protocol data units. When we take a look at layer 1 of the OSI model, right, we have network interface cards and hubs. Hubs are considered dumb devices, and I think that might have been covered last week. And the reason for that is that there's no segmentation, right? We have something called broadcast and collision domains. Everything is a collision domain on a hub, meaning that like if you plug 5 users into a hub, again, there's no segregation. Everyone's trying to transmit. It's causing collisions, right? There's again no individual doorways for each computer to speak through. At layer 2, there's a lot going on in layer 2. That's why we have the logical link controller and the media access controller, right? This data link is kind of broken into 2 different layers. But what I really want you to memorize from here is that, hey, bridges and switches reside at layer 2. Layer three, actually, let me back up. Another note for layer two. We have something called physical addresses, right? And a physical address is your MAC address, right? Also known as a burned in address, but that is like a address that is basically pre-configured for your network interface card. Nothing you can do to change that as of right now, right? There's software you can use to do it in malicious ways, but ultimately, I want you to take away that like a MAC is supposed to not be changeable. Layer three, we have logical addressing, and that's where IP addresses occur. Okay, we have routers that occur or that reside at layer three to be able to get our traffic across the internet. And then transport layer, right here we have ports and 326. You're going to refer to them as sockets, right? And some firewalls may operate here. Layer five, we're going to be doing a lot of management at layer five, like, hey, who are we talking to? Is this session closed? Where is this operating at? Um, what are the connection details really? And then presentation, here you're going to have, formatting of information, encryption occurs here, and then application, again, that's when it's kind of rendered to that end user and made usable. So let's take a look at how this works. I mentioned everything must work sequentially, right? And so when we look at this logically at layer seven, right? So this would be equivalent to like me sending an email to you. Okay, so I'm in my Microsoft Outlook, I hit send. And so what's going to happen is the application layer is going to put on a header on the data and say, hey, this was sent with Microsoft Outlook. This should be opened in some sort of email format. It's going to pass it down to layer six. Hey, is there any encryption or anything else, right? Whatever data at layer six needs to be appended there, any options, it's going to be added in this header. And then it's going to be passed down to layer five, where it does the same thing. It adds its own header, instructions, if you will, for the recipient end to open that up. And it goes all the way down the stack. Every layer is adding their own header. And then the ones and zeros, the binary. This is where it's, literally transmitting across the cable to the end user, where everything has to be reassembled. So once a full packet frame gets to the end destination, it has to go up the stack, right? And so here we're going to read at layer two, we're going to read this header for any instructions that need to occur at layer two. It's going to execute those, then pass it up to layer three. At layer three, we're looking at the instructions and then we're executing and passing it up until it gets to your desktop and you can open that up via your email client. So again, layer seven, providing supplies the network services to the end user applications ultimately, okay? Providing data to and obtains data from the presentation layer. Here are some protocols that we see. HTTP, Hypertext Transfer Protocol, File Transfer Protocol, and Simple Mail Transfer Protocol. Okay, those all fall within the application layer. At layer six, the presentation layer, again, this is a pretty simple layer where ultimately it's doing formatting of information, right? So if you're sending a picture across, right, that has to come across as like a JPEG, GIF, MPEG, MP4, like whatever the file is, the presentation layer is handling that to make sure that end user can open that up and that it's formatted appropriately for whatever program that needs to open that or interface with that. Well, I skipped session. So session layer, again, this is the management layer, right? We're trying to understand, or not understand, but track initiation and teardown of connections, okay? And so ultimately, think of session as we're just managing, ultimately, right? Who am I talking to? Is the connection still open? Does it need to be closed? Have I received commands for this to be closed or shut down? And really that's kind of the bulk of what it does. At layer four, here we have the transport layer. So a lot goes on at the transport layer. And the two protocols that you're really going to be familiar with at the transport layer are going to be TCP and UDP. So transmission control protocol and user datagram protocol. We're going to talk more about TCP and UDP, I think in this presentation specifically. But those are two that you need to spend some time studying to make sure that you memorize exactly what TCP and UDP are. Now, over here on this picture, you're also going to see SPX and IPX. Those were net novell specific protocols, and really that networking model has been deprecated at this point. So we talked about TCP, UDP. Yeah, so depending on what protocol you're using, you may have the ability to do error recovery, flow control, so making sure that you're sending enough information to the like your destination, that you're not overflowing their cup, so to speak, but there's also not a lot of room for you to put more water in the cup, right? You're trying to find that balance of how much information can I send to that other end user. And then retransmission, sometimes errors occur in data transfers. And if you're using something like TCP will help you, really kind of, what am I trying to say, transparent to the user, fix or reorder data so that it can be, passed up the stack, basically. So layer 3, the networking layer. So this is where internet protocol occurs, right? We also have ICMP, Internet Control Message Protocol. I already talked about IPX. Layer 3, you need to absolutely memorize that routers live at layer 3. And so what this picture is trying to show you too is like whenever I hit send on my email, right, to you, it's going down the stack. And that first hop router, which is likely going to be our default gateway. So at your house, that's probably the all-in-one device that your internet service provider gave you, unless you went and bought something different. But so that would be our default gateway. And so what it's going to do is that router is going to read only up to layer 3 because that's where our logical addressing is, where it has an IP address. And your router is going to say, hey, I know that this IP address is not attached to me, but I know where it needs to go because routers talk to each other to get your traffic to where it needs to go. So it sends it to that next router, right? Where that router only opens it up to layer 3. It checks the IP address. This router says, hey, it's not connected to me, but I do know where to send this. So I'm going to forward it out another port. The last router says, hey, I recognize this IP address. I'm going to send it to, the computer that's in my network and deliver it. And that's what it does. Layer 2, the data link layer. So this is where Ethernet, or ATM, stands for asynchronous transfer mode, right? This is from a device standpoint where our switches are going to reside. Bridges can really fluctuate between a couple of different layers. But switches, I absolutely need you to memorize, operate at layer 2. And at layer 2, we also have physical address. So I talked about logical addressing at layer 3, physical addressing at layer 2, which is a MAC address, or media access control address. And there's some examples in this presentation later on of what a MAC address looks like. And then finally, physical layer. So here we have Ethernet, token ring, bus topologies, right? A hub or a repeater are considered a layer 1 device because they're dumb devices. They don't really, again, do any segmentation or really any routing. It's just kind of like a way to, a hub can allow multiple computers to connect into the hub. Again, all in the same collision domain. So it doesn't scale. And then a repeater just, again, is going to allow you to get further distance on maybe your Wi-Fi or, if you're running cable. All right, I'll pause there. That was kind of a lot, but any questions, comments, or concerns over the OSI model? Okay, take that as a no, but hey, key takeaways. You need to know physical addressing, logical addressing. You need to be able to memorize the devices that reside at least the first 3 layers, right? So hub at layer 1, switch at layer 2, router at layer 3. IP addressing occurs at, I just mentioned logical and physical addressing, but IP is layer 3, MAC is layer 2. Um, we have lower layers being at transport and below, the upper layers at 5 through 7. And those are kind of the critical points there. And as we talk more in this presentation, we'll kind of peel back some of the other layers like TCP, UDP, and how does that really work and stuff like that. All right. So let's take a look at TCP IP model. So in some ways it's simpler, right? This is a layer 4 or a 4-layer model. Note that because we're talking theory a lot with TCP IP, and I know that that's technically the implementation, but there is a 5-layer model out there for TCP IP, right? Here we're focusing on a 4-layer TCP IP. And where some of this kind of gets squishy is like ARP, doesn't this can fit depending on the way you're looking at it in layer 2 or 3, right? Because we're trying to resolve an IP address to a MAC address. MAC addressing is going to work at that link layer, right? Because if you recall, the link layer corresponds to layer 1 and 2 of the OSI model. So not to go down a rabbit hole, right? But understand that as you begin to be inoculated more and more to this type of material, you may find that, hey, like there's different modes of thought, I think is really what I want to really put out there, right? But ultimately, TCP IP initially developed by the Defense Advanced Research Projects Agency way back in the day, right? Very, again, similar to the OSI, but this is the implementation and supposed to be less theory. Also less rigid than the OSI model, right? The OSI model is very focused on making sure a protocol fits exactly in a specific layer, almost in a militaristic way. Whereas the TCP/IP model we see with ARP, right? ARP layer 1, 2 in the TCP/IP model. Again, kind of depends there. But let's peel back some of the layers. So if you recall, the application layer is going to correspond to the first or I'm sorry, the highest 3 layers, 5 through 7 of the OSI model, right? So we have application here. Hold on, I think I have a fancy cursor. So application here is going to correspond to application, presentation, and session. So again, what's occurring at the application layer of the TCP IP model is we have management going on, right? Who am I talking to and why am I talking to them? Presentation, like let's make sure that the data is in a format that can be opened by the end user, and then making sure that the application data is there and can be rendered appropriately to that end user. So all of that is jammed into the application layer of the TCP IP model, right? So we see again, just highlighting some important stuff here: session establishment, maintenance, and termination, right? We talked about some protocols that were in the OSI model, but same things here, like net BIOS, BIOS being basic input output system, multi-purpose internet mail extension, transport layer security, secure socket layer, file transfer protocol, domain name service, hypertext transfer protocol, and simple mail transfer protocol are some of the acronyms down there. Transport layer, again, this was a 1-to-1, right? And we're doing the same stuff as the transport layer in the OSI model. Okay, this is where you're getting sockets, you're getting ports, you're handling transport protocols like TCP and UDP. Internet, again, a 1-to-1, right, of layer 3 in the OSI model. So here we have logical addressing. You see that again, which is just a fancy way to say internet protocol. Okay, you have internet control messaging protocol, ICMP. There's a lot of different variations of ICMP, but what most people are probably going to be familiar with ICMP is going to be ping, or echo request and echo reply, as it's more formally coined in the internet group messaging protocol. And then finally, we have the link layer in the TCP IP model. So this corresponds to layers 1 and 2 in the OSI model. Okay. You may also see this referred to as the network interface layer. And all the same stuff has happened, right? You have physical addressing. You have the information actually being transferred across a wire to get to its end destination, right? line coding and bit synchronization, modulation, especially given Wi-Fi antennas, frame synchronization, error detection, and correction potentially. Some of the things that you see down here, address resolution protocol, I kind of talked about that a little bit more. I think we have some slides that'll really explain ARP. So I'll wait until that slide. But then NDP is a really cool feature for especially like Cisco devices. If you take a Cisco device, whether it's a switch or a router, and plug it into another Cisco device, those devices immediately start talking to each other and they start saying, "Hey, what routes do you know about?" Or, what is in a switch? It would be like, what does your cam table look like, right? So who do you know and how are you routing your traffic across the local area network? IEEE 802.3 is the spec for Ethernet, and IEEE 802.11 is going to be for Wi-Fi. So ultimately, what are the differences, right? Ultimately, so with OSI model, going to be protocol independent, right? It's going to be rigid, 7-layer model. It can be somewhat of a problem trying to militaristically fit protocols into a particular area because we have things that kind of operate and could really, by definition, fluctuate between. But the OSI model doesn't work like that. Whereas the TCP/IP model, again, 4-layer, right? It's not militaristic. It's a little squishy in some areas. It is based on standard protocols, and ultimately, it's kind of I should say, protocol dependent, and is the implementation of the theory behind OSI. All right, so here's where we're going to start defining out TCP, UDP, ARP, and some other protocols. So let's first look at TCP, or Transmission Control Protocol. This resides at layer 4 of the OSI model, right? It's going to be connection based, right? Making sure that we get reliable delivery ultimately, okay? So when you think TCP, there's something called a 3-way handshake, which we'll also get to here in a second. But that 3-way handshake basically says, like, hey, I want to talk to you and I want to make sure that you're going to get the information that I'm sending you, right? And that's the end computer talking to the server or the other computer, however the connection is set up. And then once that 3-way handshake occurs, then both sides are on the same page. And they share a lot of information back and forth, which you'll see in 326 with like sequence numbers and acknowledgement numbers, where I'm sending you data and you're sending me acknowledgments back to say, hey, I'm getting that data. And there's protection mechanisms put into place that basically say, hey, I didn't receive an acknowledgement for that data. It must be lost. It must have gotten corrupted in transit and was not received. So I'm going to go retransmit that, right? TCP allows you to do that. And sometimes frames arrive out of order, right? So you might get, instead of getting 1, 2, 3, 4, it might come 1, 4, 3, 2. And then what TCP is going to do is it's going to recognize that based off sequence and acknowledgement numbers, and it's going to place it back in order so that it can be reassembled the right way up the stack. So TCP is kind of a heavy hitter. Now, this looks like a lot, and you don't need to memorize this, okay? But this is just to show you, because here in a second, we're going to talk about the UDP and what that looks like. But there's a lot going on here, right? This is a lot more complex than UDP. It's not ultimately very complex, but when you look at the difference, but let's go ahead and do that between UDP, right? Like very vastly different, right? So a lot more overhead ultimately. So what a TCP header is going to look like, we have our source port, destination port. I've mentioned sequence and acknowledgement numbers. So that's like we're numbering the data we're sending, and we're also getting a number back from the end user to say how much data has been received. Reserve space, offset, and then flags, right? Some important flags that could be set there. We have, if there's congestion, that could be indicated there as well. There's also urgent, right, which isn't really used anymore. Acknowledgement, push, meaning like, hey, don't wait for the additional packets that may be fragmented here. Reset, synchronization, and finish, right? So reset's going to reset the connection. Synchronization, we'll talk about here in a second in the next slide on 3-way handshake. And then finish, it's like, hey, we need to tear down the connection. We're all done here. All right, so TCP 3-way handshake. So what you need to remember here is syn, synac, and ack. Okay. Synchronization, acknowledgement, and acknowledgement. Now, the numbers used in this example are going to be 100% arbitrary. So please do not get wrapped up in the sequence number and acknowledgement number. Okay. So what's happening here is, this computer wants to connect to this server. And so it's going to send out, the equivalent of a, hey, how's it going? I would like to talk to you. That's the synchronization uh, flag in the TCP header. The sequence number is going to start at, again, arbitrary number, but 1000 here, an acknowledgement of 0. The acknowledgement of 0 is because I haven't received anything from the distant end. I'm labeling the data that I'm sending starting at 1000. So the server takes this synchronization and says, oh, hey, the client wants to talk to me. I should probably acknowledge them and say, hey, yes, I can talk to you too. So that's what the synchronization acknowledgement is. And so they can't start at the same sequence number because that wouldn't work, right? So the server is going to start at 2000, again, arbitrary. And when you start looking at the actual traffic that's going back and forth, they're usually very large numbers so that there's no um, collisions per se. So server's using sequence number of 2000, and it's going to do an acknowledgement of the data that was received, right? So that's where we get the 1000 plus 1, because the plus 1 is saying I've received 1000 and below, okay? That's how that number was derived there. So then the computer gets that, hey, I can talk to you. And so the client is going to basically say, okay, I'm about to start transmitting, right? Or I'm about to start telling you my problem. And so that's where this acknowledgement comes into play. Now we're going to do our sequence number plus 1 because it's our next transmission. And we're going to acknowledge the sequence number sent from the server plus 1 to say we've received 2000 and below. Okay. At that point, once that send, synac, act transaction has occurred, the session is established, right? And now we can have reliable data transfer between the client and the server. And once we need to turn that off, right, we can send a TCP flag, a finish, to basically break down that connection. I'll pause. Any questions, comments, or concerns? Okay. So let's move on to UDP. Now, UDP is the complete opposite. UDP does not care at all if you get your data. It doesn't care how fast it sends it, right? Like UDP is just like going to try and get you the data as quickly as possible. And if you lose some along the way, it doesn't care. There's no retransmission, there's no reordering. Like again, UDP is like the honey badger of the protocols. Like it, as long as it got there, it's like quick math, right? 3 plus 3 is 8, right? Like it wasn't necessarily right, but it was fast. And so this is what the UDP header looks like. Again, very simplistic when compared to TCP. We have source port, destination port, length, and checksum. And then what is UDP used for? Like gaming is a really good example. We have DHCP, or Dynamic Host Configuration Protocol. DHCP, I don't think we've talked about in this class, but it is a way for you to be assigned an IP address on a network. There's voice over internet protocol. So really any kind of, whether it's a soft phone or a hard phone, leveraging VoIP. So think like Skype back in the day, or I think, what are the kids using now? Like Discord or I don't know, Microsoft Teams, whatever you make calls on nowadays, like voice over IP, IPTV. Like ultimately, if we had to use TCP for those things, it would be kind of nuts, right? Because if you've ever been on a call where, I don't know, the person's signal starts dropping, right, and you start missing some words, like TCP doesn't work like that, right? You can't just drop communication, right? It's going to ask for a retransmission. So it's going to stop the phone call, ask you to make sure that you restate what you just said, right? That way it can get that data to the end user, right? Or it's going to try and reassemble data to get back, and then you're going to be in a delay, right? So it's not really suited for being able to use TCP for like voice over internet protocol. And so that's why UDP is going to be used for like phone conversations. But ultimately, what you need to take away from here is UDP is not reliable, but it's fast. So let's talk about IP, right? Internet protocol. Again, layer three of the OSI model, this is called logical addressing. And you can think of this as almost like a post office where everyone has their own address. Now, it is definitely a little bit more complicated than that, okay? We have publicly routable IP addresses and we have private IP addresses. Now, every device that's behind your internet service provider all in one device is going to have a private IP address, right? Your Kindle or your iPad is not going to reach out directly to a server on the internet. Long story short, what ends up happening is that all-in-one device given to you by your internet service provider has one publicly routable IP address. So no matter if you're using your desktop computer, your laptop computer, your Kindle, your iPad, whatever it is, all of that is seemingly going to look like it's coming from one IP address because once that traffic hits your default gateway or that all-in-one device that you get from your internet service provider, it's going to do a translation and say, hey, 192.168.1.1 on this internal network, right? And I'm referring to like a Class C private IP address here, is going to be this person's iPad, but it needs to have the public IP address. So we're going to keep track of this session and we're going to reach out to the server they're trying to get information from. Okay. That might have been a little bit more in depth than you necessarily needed to know, but like the big takeaway here is we have publicly routable IP addresses and private IP addresses. Okay. And for each household or organization, generally speaking, there's only one publicly routable address. Everything else has to do something called NAT, network address translation. So what is IPv4? Where the heck did IPv5 go? And what about IPv6? Okay. So IPv4 is is currently very ubiquitous. Okay. Almost everybody here, in fact, I doubt anybody in this class is running native IPv6. I could be wrong, but it's very rare to see someone running native IPv6. IPv4 is currently like what we're using. And so this, when it was developed, the scientists who were developing IPv4 could have never imagined how the internet would have exploded the way that it did, right? And so it was ultimately very limited in the amount of addresses that can be sent out, right? Or assigned, I should say, right? So we see limited to approximately 4.2 billion unique addresses for IPv4. And that was really a really limiting factor for IPv4. But they started recognizing in the, I would say, early to mid 90s that, hey, this is going to be a problem. The internet's getting much bigger, and the way that we're growing, I don't know if this is going to be sustainable, right? And so, I forget the story on IPv5. Ultimately, was never really a thing, right? We went to IPv6. Actually, I take that back. IPv5 was still a 32-bit address scheme and was not going to address all of the problems that we needed. So then IPv6 thought started taking traction, and you'll see like the number of addresses that IPv6 utilizes is astronomically more. In fact, in some spaces, you'll probably see this quote where every grain of sand on Earth could have its own IPv6 address. It also changes the way that it's represented, right? So we have dotted decimal notation for IPv4, and we use hexadecimal notation for IPv6. You can see there's not an IPv4 address here, but we see this is a IPv6 address and what it looks like, and it has hexadecimal representation. Whereas if I go to PowerShell and I do ipconfig, we'll just do ipconfig normal, IPv4 dotted decimal notation, and then we have IPv6 hexadecimal representation here. Okay. So IPv4 addressing here, we talked about dotted decimal, 32-bit. The way that these numbers are derived, right? So an example IP address of 195.143.67.2. Okay. We have binary representation above this. Okay. So again, the bottom number, 267.143.195, that is the IP address. They're in blocks called octets. So each one of these blocks are considered an octet. Above this is binary representation. So what binary looks like, here we have binary place values. Okay. So this 0 corresponds to 1 here. Okay. So moving over, this 1, which means the bit is on, represents the 2. And then so it doubles every time. We have 4, 8, 16, 32, 64, 128 as we go right to left in binary notation. The reason this number is 2 is because that bit in the 2 space is on. We see the place values here, right? 1, 2, 4, 8, 16, 32, 64, 128. All the other bits are off except for 2, what represents 2. In the next octet, we have 67. So the 1 bit is on, the 2 bit is on, and the 64 bit is on. And we see that here, right? So 64 plus 3 is 67. Okay. And same for the other 2 octets. That's exactly how that is calculated. Here we have public IP addresses, IPv4 addresses specifically. Okay. They're broken up into classes. So a class A is one, we haven't learned like subnetting yet, but look at the sheer number of hosts, right? Sheer number of 16 million hosts can be put onto a class A address. So very, very large for class A. Class B scales that down a little bit, and then class C is the smallest of that. But you can subnet this much more as you go from A to B to C. Okay, and subnetting allows you to basically break up networks, if you will. So number of hosts on an individual subnet is really 255 or 254 really, because 255 would be broadcast. But just the main takeaway here is that there's different classes of IPv4 addressing. A is very big, B is medium, and C is small. Now D is considered reserved, and E was for experimentation. All right, so next we have a PIPA, or Automatic Private Internet Protocol address. This is an address assigned by your operating system whenever DHCP or some other IP address has not been specifically assigned. And this is the address range for which an APIPA address will fall in. It's non-routable, so it's very much like a private IP address. But if you're connected to a hub and there's other computers connected to the hub, it does allow you to communicate within that work group or that peer group. This is an example of what an IPv4 header looks like. Again, this is not something that you necessarily need to memorize, okay? But version here is going to be either 4 or 6, and for this specific header, it would be 4. We have, how long is the header length, right? What is the type of service that's being provided? What is the total length of the overall header or message? Identification. We have flags that can be set. Fragment offset. So if there are multiple packets that need to be received at the end, it's going to say, hey, this is 1 of 10, 2 of 10, 3 of 10. Time to live. Time to live is the concept referring to like, your data can't travel across the internet forever. And so the standard TTL is 225 hops. And so basically what that says is, your data can traverse 225 different routers that it needs to get to its end destination before when that TTL hits 0, that data is going to get dropped. Otherwise, you're going to have traffic kind of circling the internet forever, causing a storm, right? Collisions and an absolute mess. What protocol is in use? A header checksum is just a cryptographic way to say, is this data trustworthy? But when we look at IPv4 header and really IPv6 and anything that uses a checksum, this is very rudimentary. Source address, destination address, and then any other options that might be configured. This is what an IPv6 header looks like. So we trim it down a little bit. So here in the version, we have 6 instead of 4. traffic class and flow label are nice because that provides you a concept called quality of service. Now, quality of service is basically where you get to prioritize your own network traffic and say, hey, if we have a very busy network and I need to make a phone call, make everything else stop or hold it off until we have more bandwidth, but that phone call needs to go through. Payload length, next header, hop limit, right? Very much like TTL. The source address, destination address. Again, this is not necessary. These two slides, along with the TCP and UDP headers, are not meant to be memorized. I know that it can look like a lot, but they're just for the inoculation aspect. So what are the benefits of IPv6? Well, we have more addresses than we know what to do with ultimately, at least for right now. You don't have to do network address translation because everyone can have their own IPv6 address. It does a lot of administration that we used to have to do with IPv4 is no longer a thing, such as like we don't necessarily need DHCP anymore, right? No more private address collisions, which is very much a thing. Quality of service is another massive benefit to IPv6, right? Where we get to say, hey, we're prioritizing certain types of traffic. Authentication, privacy support. Ultimately, it is going to be much less of a burden. Now, IPv6 has been around for a really long time. Adoption, though, is not great. And let me show you this real quick. All right. So on 2 days ago, November 17th, 2024, native IPv6 traffic that traversed google.com was only 44.62%. And that's global. Okay. And when we look at per country IPv6 adoption, you can see like a decent part of the world has very little adoption, right? Like the United States only has 47.830% IPv6 adoption, right? And you can hover over any of these countries. I'll drop this link in the chat so you can take a look. But the reason here that IPv6 has, I don't want to say failed because it's not failed, but the reason people don't want to adopt it is that we were able to extend the use of IPv4 through a lot of different technologies like NAT and PAT. So network address translation, port address translation. And it became not so much of a concern that we had limited addresses for IPv4. There's also a whole mismanagement of IP address allocation that occurred with IPv4, but I digress. But so all of that is basically to say that IPv6, people are very slowly adopting it. One, because in a lot of cases, people have to spend money. And, if I'm a business, I'm going to say, why am I going to spend this money when IPv4 is working just fine for me, right? So that's kind of the prevailing thought. And there's been multiple initiatives, I would say, like there's been like global and national move to IPv6 days, but you can see like we're still really not there in terms of adoption. But I will say in the nearly 20 years that I've worked in this field, I have seen IPv6 adoption grow tremendously. I mean, I can remember a time when IPv6 was like you did ipconfig on your computer and you didn't get an IPv6 address, right? Like internet service providers were not just issuing those. But now, it's there. You go to your Windows or your Mac machine, go to terminal, and you look at your IP stats. I mean, you're going to have IPv6 addresses, and most people are running both at the same time. That way, they can interface with all the architectures. All right. All right. So let's look at what IPv6 addressing looks like. And this is just for your knowledge. You don't need to memorize this per se. This is good knowledge, but so there are a couple different rules we can use with IPv6 addressing to make it more palatable, I would say. We can drop leading zeros in each octet. Okay, so here we don't have any, but we have a leading zero here in the second octet. So you can just drop those, right? And you would start out with this as the full address, but it can be truncated down to just this, which is kind of nice, right? We couldn't do that in IPv4. There's also the zero compression rule that we can use, meaning that, if there are multiple zeros, we can just add a double colon and completely omit all those zeros because now we understand that, all of these octets, so what, three different octets are just zeros. So we take this entire address that's kind of cumbersome to write, and it becomes a little bit more palatable. Now, and then you can also combine both of these rules together, right? So again, we have our very long IPv6 address here that can be truncated all the way down to just that. All right, so let's talk about ICMP. So ICMP stands for Internet Control Messaging Protocol. And again, most people are going to relate this to ping. The more formal name is echo request and echo reply. From a network administration point, this is really for diagnostics, like reaching out and being able to see if you can touch another computer or a server or the internet, really, right? Is what most people use ICMP for. Now, ICMP is like a Swiss Army knife, okay, because it can do a lot of different things, right? The spec for ICMP, and I forget the exact RFC or request for comments number that talks about everything ICMP can do, but it's broken up into types and codes, and we'll see that on the next slide here. So this is what the header looks like. Again, I don't need you to memorize this, but what I do want you to take away from here is that ICMP leverages types and codes. So a type 0 code 0 is an echo reply. And that's the information that I'm getting back to me when I do a ping to wherever. So let me pull up PowerShell here. And if I ping quad 8, which is a Google DNS server, right, these replies are echo replies that are being sent back to me. I sent an echo request, which is equivalent to me being like, hey, can you hear me? And then the server being like, yes, I can hear you, but it's going to tell me that 4 times because that's just how the spec works. But you can see like a lot of different types and codes associated with this. So type 8 code 0 is echo request. This is what a ICMP header leveraging ping or a type 8 code 0 will look like. Again, nothing super fancy here. We're just plugging in the numbers associated with the RFC, right? So it looks like RFC 1122 is that for ICMP. Here's some other examples. Time exceeded message, type 11 code 0, type 13 code 0, timestamp message, and then we have a timestamp reply at type 14 code 0. Destination unreachable, which would be a type 3 code 0 that would occur if like you don't have connection to that in destination system. But anything that can be used in a security fashion can also be used against them, right? So ICMP is going to also pose some security risks. ICMP is something that you do not want to allow to occur from the internet to your internal network. And so some things that could occur, right? ICMP responses themselves, one, show that, hey, there's a computer here, but also depending on the response that you get can also give indications of a potential operating system that it's running, or certain conditions that have been set on that computer. Okay, so just a response by itself can give indication of deeper messaging. Flood ping, which isn't as much of a concern nowadays, can be used to execute a denial of service or a distributed denial of service if you have multiple computers participating in this, where you essentially you can craft pings to have a very large payload. You try and overload a computer so that it cannot respond anymore. And then wake on LAN, right? So if this is being executed, if a computer is asleep on a network and you send it an ICMP packet and it wakes up and is able to respond, then again, it's providing its presence on the network, and it's also providing some of that deeper level messaging depending on what's configured on the computer and whether or not, if it's a Windows machine or it's a Mac machine or a Linux machine, they all have slightly different variations in the response. So that can give an attacker an idea of maybe follow-on actions. Let's talk about MAC address. So we mentioned this earlier. This is going to occur at layer 2 of the OSI model, layer 1 in the TCP/IP model. But well, actually, let me back up here before we get to just MAC addresses. You probably have heard me say this multiple times at this point, and you're probably sick of me saying it, right? But it's something you need to know. Logical addressing, IP, physical is MAC. But let's talk about MAC addresses a little bit more. So this is what a MAC address will look like. And the first half of the MAC address is supposed to be specific to the vendor, whether that's Dell, CyberPower, IBM, doesn't matter, right? And then the serial number is supposed to be specific to that network interface card, okay? So these are broken up into organizationally unique identifier, right? That's the vendor number versus the universally administered address. Now, you're not supposed to be able to change this, but as I mentioned, there's software out there that allows you to change it, and it's usually for malicious purposes. Now, how does a MAC address really allow us to route traffic across a local area network? Well, this is what it will look like. And ultimately, I know this says router, but it's more appropriately should probably be labeled switch. But what's going on here is that this computer is sending an email out to this web server, okay? So the IP address of our computer here is .11. I'm just going to say .11, even though it's 195.15.16.11. And then the default gateway here is 195.15.16.1. That's going to be important in a second. So again, we see the IP address here. The MAC of our network interface card is here, ending in 2039. So whenever we send this email, right, it's going to have a source IP of our .11, a destination IP of .198, which is the web server up here. Okay, I'm getting the .198 from up here. That's our destination, who we want to ultimately reach out to. And then source MAC is 2039. Okay, so that's the network interface card on our computer. And then our destination MAC is not going to be up here, right? So D26C is the destination MAC address. Instead, the destination MAC is F4C7, which is going to be this port on the router. It is our first hop, our default gateway, if you will. Okay, and so that's where the destination MAC is going to be labeled. Now, the router receives this information. It takes a look at the source IP, the destination IP, and the source MAC address, and the destination MAC address. No, source MAC, right? And then it's going to strip the destination MAC as well as the source MAC on that, and it's going to forward it out this other port. And so now the email is going to have a source MAC of F596, which corresponds to this port, like where the email is leaving from out of that router. The destination MAC is going to be this next router, the next port that it has to do for its next hop. So 0119, we see that here. So this router is going to do the same thing, right? It's going to take a look at the source IP, the destination IP. It's going to strip the source and destination MAC. And the destination MAC is ultimately now like where we want to go, right? The D26C, which is our web server. And the source MAC is still going to be this port, that's off of the router. So 57C2. Source and destination IP address stay the same. And then it is able to deliver that message. All right, let's talk about ARP real quick. So address resolution protocol is how we map IP addresses to a MAC address. And I don't like this slide per se because I think the next one explains it a little bit better. So host A wants to talk with host B. And so what's going to occur is host A is going to check their ARP cache. And then it's going to say, hey, I have a MAC address, but I need the IP address that corresponds to the MAC address. So the ARP request is sent. Now the ARP request is going to go to everybody on the network, right? But not everybody's going to action it. Host C is going to be like, this is not my MAC address. So I'm going to discard the traffic and I don't need that. Okay. And then, so that goes out. Host B gets that. It's also going to update its ARP entry, right? And it's also going to reply back to say, hey, this is my IP address with my MAC address, right? And so that's going to go back to host A. Host A is going to log that in its ARP cache, and then it's going to be able to send information as necessary to host B. Next, we have Border Gateway Protocol. And Border Gateway Protocol is ultimately going to be the backbone of the internet. This allows routers across the internet to be able to share routes and be able to essentially allow you to be able to get to where you need to go on the internet. Okay. BGP is a router specific protocol that, again, is going to allow exchange of routing information because ultimately, routers may be disconnected from certain edge areas, and those routes have to update essentially constantly. And so this is kind of what it looks like logically, right? We get updates from neighbors constantly. I think for Cisco routers, it's like every 30 seconds, they're basically sending a beat to say, hey, is this connection still alive? And if something gets pulled and it's not getting an answer back, then it says, hey, I got to delete this route out of my table, right? And that's where we get discarded routes. But if we're receiving routes, then it's going to keep it in that BGP table, right? These are all known routes from neighbors and basically where I'm going to send my information next. And routers are all about efficiency and making sure that they're taking the most efficient path possible for your data. All right, next we have DNS, domain name system. So this is an awesome system that was developed so that we don't have to remember IP addresses for every website that we go to. Instead, we can remember google.com. But that's not how computers talk. And so the computer is going to need the IP address to where it's going. But DNS allows us to put a name to that IP address so that when we put it in google.com, the computer can say, hey, let's go get this IP address. Okay, so let's talk a little bit about how DNS works. Well, the way that the hierarchy here is that we have a DNS recursive resolver, right, which we'll talk about here in a second on the next slide. We have a root name server, a top-level domain name server, and then an authoritative name server. Now, the root name server is kind of the boss in this entire situation where it's going to basically say, hey, I don't know where example.com is, but I know where the .com servers reside. And so the TLD is going to be the .com, the .edu, the .ru, the .cn, all of that, like, end of your URL is going to be considered the top level domain. And then the authoritative name server is going to be like Cloudflare, Arizona, .edu, right? .edu being the TLD, but the authoritative name server being like Arizona or whatever you want to website you want to go to, example.com. So ultimately, the way this works, right? I want to go to example.com. I'm going to go to my DNS resolver, and ultimately, I'm checking in cache first. Cache being like things stored in memory. And I'm going to check in my operating system to see if it's stored in cache. And in this situation, it's not, right? So we're going to go to our DNS resolver and say, hey, I don't have the IP address for this website. Can you help me out? And that's where we have the recursive query, right? Where the DNS resolver is always just going to go and do a bunch of work for us. That's what that means. So the iterative queries then start, right? So the DNS resolver says, I don't know the IP address either. Let me go to the root. Hey, root, where's example.com? Root is going to say, hey, I don't know where example.com is, but I do know where the .com TLD servers reside. Here you go. Go ask them. So then the DNS resolver says, all right, cool. Let me go to the TLD.com servers. Hey, TLD.com server, where's example.com? And the TLD servers are going to be like, hey, I don't know exactly where the IP address for example.com is, but I know where example is. Well, let me send you the area for that. So then DNS is going to say, okay, well, let's go to the authoritative name server, example.com. What is your IP address? And then it's going to retrieve that information. It's going to store it in cache, and then it's going to allow us to be able to go to that server and get information. So DNS troubleshooting, right? So this is something that you can actually potentially implement, right? Where a DNS server will have a problem, some sort of error, failure, or whatever it is. Okay, the symptoms I would say is if you could type in an IP address and go to a website, but you go to type in google.com and you get nothing. Okay, I've seen this actually occur, and again, if it goes to a website based off an IP address, but it's not able to resolve the name, it's a DNS problem. And so, what you can do in this situation is that you can go and go to your configuration for your IP addresses and configure a DNS server to either be the DNS for Google, which is quad 8, 8.8.8.8, which we pinged earlier, or a quad 9 public DNS server, any public DNS server really by any company that's hosted, and then try it again. See if you can go to google.com. And if you
So
can, that means that the DNS server that's configured for your network is not working appropriately. Okay. And so that, again, you'd have to go troubleshoot your DNS server.
so Professor, I have a question.
Yeah, what's
So
up?
if so like say if he's going to the library to do homework and he's logging onto their
I can like hardly hear you, Shannon.
I'm sorry. Can you hear me now? Is that
Barely,
better?
slightly.
What about now? Okay. What if you're going to a public place, like to a library, you log into their website, to their Wi-Fi, and get that same issue, like try to log onto like Google, and it says DNS issue. Is that similar to that?
I still can't get the gist of your question.
I'll,
It's so
I'll,
like soft spoken.
okay, I'll go ahead and do it. I'll type it in my email. That's fine. Sorry about that.
Okay. Sorry, Shannon. Um, okay, so ultimately, what did we talk about today? We talked about DNS, we talked about IP, we talked about the OSI model, the TCP IP model. We talked about some specific protocols like Border Gateway Protocol, TCP, UDP, ARP. Okay, um, a lot of information being thrown at you, and some things I want to make sure and go. I should have hit this earlier, but this you will have a question on your quiz on how to convert binary to dotted decimal. You will not be asked anything about this, and you will not be asked anything about this, right? So, with a PIPA or where's the other slide? Compression rules for IPv6. So, those were for your information. So don't spend, I mean, it's important information, but like it's not going to be on your quiz. Okay. Is I think what I'm ultimately trying to say here. Um, you need to know three-way handshake. That is a critical concept. TCP, I'm sorry, yeah, TCP and UDP critical concepts, ARP critical concept. Those are some of the areas I would absolutely make sure I spent some time in. You're not going to need to know type code on your quiz. You will get asked a question about security risk for ICMP. DNS is a critical one. But those are some of the areas that I'll absolutely highlight for you. Any other questions, comments, or concerns?
Yeah. Where can we find the hardware that's linked with the different layers?
What do you mean? So like you
Like,
mean on the slide?
yeah, I didn't see, I didn't notice if it was on the slide or not. But like you said, like layer two is a switch, layer one is a hub. Is there anywhere where I can see that again?
Yeah, on slide 5, where it says OSI model, it shows like a hub is a layer 1 device, switch layer 2, routers layer 3.
Oh, okay, got it. Thank you.
Yeah, yeah, absolutely. I think it also shows it in these slides as well. So like 8 through 13, 7 through 13. No, more like 8 through 13. And you can see that off to the side here where it's switch, bridge, layer 2, hub, repeater, layer
Oh,
1,
got it.
router, layer
Yeah,
3.
it was just small, so I couldn't read it. Thanks.
Gotcha. Yeah, of course. All right, guys. Well, if anything else pops up, Shannon, are you sending me an email with your question so that I can answer it?
Yes, I'll go ahead and do that. It's not a problem. Yes,
Okay,
I
sounds
will
good.
go ahead and send you an email. So yeah.
Okay, sounds good. All right, guys. Well, I wish you the best of luck on your quiz for this week. If you have any problems whatsoever, please let me know. Or if you just have any questions whatsoever, please let me know. So I hope you have a meritorious week, and we will talk soon. Have a good week, everyone.